Hi, and welcome to Module 3, Introduction to Solidity. So far, we've learned what the blockchain is, we've understood the EVM, and now we're going to write an actual smart contract. This is the module where theory becomes practice. We're going to learn Solidity, the programming language for Ethereum. By the end of this module, you'll be able to write a complete functional smart contract, one that you could deploy to Ethereum today. Let's get started. So what is Solidity? Well, if the EVM is the CPU, the processor we learned about in Module 2, then Solidity is the programming language we use to write programs for it. You do not write in opcodes. You don't write in bytecode. That would be like writing in assembly language. It would be incredibly tedious and error-prone. Instead, you write in Solidity. It's a high-level language designed specifically for smart contracts. You write code in Solidity, you pass it to a compiler. The compiler translates it to EVM bytecode. Those low-level instructions the EVM understands. That bytecode then gets deployed to the Ethereum network. Solidity is statically typed, which means every variable has a specific type, and the compiler checks types at compile time, catching errors early. It is contract-oriented. The main building block is a contract, which is like a class in object-oriented programming. It's designed for Ethereum. It has built-in concepts for the blockchain, addresses, payable functions, and events. So why Solidity? Well, first, it's easy to learn for developers coming from JavaScript, Python, or other mainstream languages. Second, it was designed from the ground up for smart contracts. It understands blockchain-specific concepts natively. Third, it has a rich ecosystem. Tons of libraries, frameworks, and tools built around it. Every Solidity file starts with a specific structure. Let's break that down. On our first line, we see SPDX license identifier. This declares a license. It's a comment. The double slash means the rest of the line is ignored by the compiler. Why do we have to include this? Well, many tools and automated systems can scan code and look for license declarations. It's good practice to be explicit about how your code can be used. MIT is a very permissive open source license. You can use MIT licensed code almost anywhere. Other options exist: GPL, Apache, BSD, but MIT is the most common type in the crypto world. On our second line, we have Pragma Solidity caret 0.8.20. This line tells the compiler which version of Solidity you're using. The Pragma keyword means this is a compiler instruction. Caret 0.8.20 is a version constraint. The caret symbol means the code is compatible with version 0.8.20 and higher, as long as it's still in the 0.8 series. So caret 0.8.20 means 0.8.20, 0.8.21, up to 0.8.99, but not 0.9. Please avoid using floating pragmas, like greater than or equal to 0.8.0. This allows any version of 0.8.0 or above, even 0.9 or 0.10 if they existed. Your contract might behave unpredictably with an untested compiler, always pinned to a specific minor version. These two lines are boilerplate. Include them at the top of every Solidity file. Now let's look at contract structure. Now the contract itself. A contract in Solidity is the main building block. It's similar to a class in languages like Java or Python. Here's the minimal contract. At the top, we start with our license identifier and then our pragma statement. Then, the keyword contract declares a new contract. You give it a name called my contract, and then you open and close curly braces. This is a valid contract. Inside those braces is where you define your state variables. This is data that persists, your functions, code that does things, events, which are logs for off-chain systems, and modifiers. These are reusable rules. Think of a contract like a class, but with crucial differences. A contract is deployed permanently on the blockchain. It gets its own address. That address is permanent. The contract will exist there until somebody explicitly destroys it. It has persistent state. Variables defined inside the contract live in storage on-chain. They survive across multiple calls. Every interaction with it costs gas and is immutable. Once you call a function and it modifies state, that change is permanent. There is no undo. That last point is quite important. You need to think carefully about what your contracts do because you can't fix bugs after deployment. Now we come to state variables. State variables are the data your contract holds. A state variable is any variable declared at the top level of your contract, outside of function. State variables are stored permanently. They live in Ethereum storage. Every node in the network holds a copy. So here we have a contract with three state variables. We have uint256 public account, address public owner, and a boolean public active. Let's break this down. uint256 is the data type. Unsigned 256-bit integer, that's a number from 0 to about 1.2 times 10 to the power 77. That's very large. Public is the visibility modifier. More on that in a moment. Count is the variable name. Address is a data type specifically for Ethereum. It represents a wallet address, a 106-bit identifier. Bool is a boolean, true or false. Here is where module 2 knowledge becomes critical. Reading a state variable is cheap. It costs minimal gas. Writing a state variable is expensive. You're performing an SSTORE operation, around 20,000 gas. This is why when you write smart contracts, you must think about minimizing storage writes. Read freely, write sparingly. As you write your contracts, constantly ask, do I need to write the storage, or can I do this in memory? Storage writes are expensive. Memory is cheap. State variables hold data. Functions define behavior, what the contract can do. Here's a simple function. Let's parse this. First, we have the function keyword. This declares a new function. Increment is the function name. The round brackets are parameters. In this case, none. Public is the visibility. We'll explain this in the next slide. The curly braces contain the function body. The body does one thing. Count plus equal 1. This looks simple, but it's doing multiple things under the hood. Count plus equal 1 is shorthand for count equals count plus 1. At the bytecode level, this executes three operations. First, sload. Loads the current value of count from storage. This costs about 100 gas. Second, add. It adds 1 to it. This costs 3 gas. Third, store. Store the new value back to storage. This costs 20,000 gas. In total, costs roughly 20,100 gas. Look at that breakdown. The SSTORE dominates. It's 99% of the cost. This is why gas optimization in Ethereum is so often about reducing storage rights. Function visibility rules. Solidity has 4 visibility modifiers. Understanding them is critical. First, public. A public function can be called from outside the contract by anyone or from inside the contract by other functions. Public is the most open. Second, external. An external function can only be called from outside the contract, not from inside. It's stricter than public. Why have both? External functions can be more gas efficient in certain situations, but that's an advanced optimization. Third, internal. An internal function can only be called from inside this contract. Inside derived contracts, if this contract is inherited. Internal functions are private to the contract family. Fourth, private. A private function can only be called from inside this exact contract. Not even derived contracts can call it. Private is the most restrictive. It's important, if you don't specify a visibility, Solidity requires you to be explicit. It won't assume. Visibility is a security mechanism. By making functions private or internal, you're saying only specific code can call this. As a contract developer, you want to minimize the surface area. Don't expose functions that don't need to be exposed. This principle of least privilege is fundamental to smart contract security. View and pure functions. There are two special function modifiers that change how gas is calculated: view and pure. A view function reads state but doesn't modify it. The function getCount just returns the current count. It reads from the count variable and returns it, no modifications. A pure function doesn't even read state. It takes inputs and produces outputs with no side effects. Here, the add function takes in the parameter and adds 1 to it, and then returns the result. No state access at all. When you call a view or pure function off-chain, meaning you're not submitting a transaction, just querying the blockchain, it costs 0 gas. When you call them on-chain, inside a transaction from another contract, they still cost gas, but potentially less than a regular function. Front ends and applications constantly call view functions to read contract state. Since they cost no gas off-chain, you can call them frequently without paying anything. As a developer, use view and pure liberally for functions that don't modify state. They signal intent and can provide gas savings. Common data types. Solidity is statically typed. Every variable has a specific type. Let's learn the most common ones. A uint256 is an unsigned integer, a number from 0 to 2 to the power 256 minus 1. That's an astronomically large number. It's useful for balances, amounts, and counts. Int256 is a signed integer. It can be negative or positive, ranging from negative 2 to the power 255 to positive 2 to the power 255 minus 1. There are smaller variants, uint8, uint16, uint32, and so on. Smaller sizes can sometimes save gas if you pack multiple into a single storage slot. Boolean is a bool. It's either true or false. Address is specific to Ethereum. It represents a wallet or contract address and is 160 bits. There's a variant called address payable, which can receive ETH. A string is text. It is dynamic size. It grows as it's needed. Strings are expensive to store because they are variable length. Bytes is a raw binary data, also dynamic, and bytes 32 is a fixed size 32-byte chunk, which is gas efficient for storage. Always try and use the smallest type that fits your needs. Use uint8 if your number is 0 to 255. uint16 if it's 0 to 65,535. This saves gas, especially in storage. But don't prematurely optimize. Write clear code first, then optimize if needed. Mappings are one of the most important data structures in Solidity. A mapping is a key value store, like a dictionary in Python or a hash map in Java. In this example, we have the balances mapping. This says each address maps to a uint256. You can look up any address and get a balance. Mappings have some important properties. Lookup is O of 1, constant time. It doesn't matter if the mapping has 10 entries or 10 million. Lookup is instant. You cannot iterate keys. You can't write, give me all the keys in the mapping. There is no built-in way to enumerate. If you need to iterate, you must manually maintain a separate array. If you look up a key that doesn't exist, you get the default value for that type. For example, the default for a uint256 is 0. For an address, it's 0x0. This is important. You can't distinguish between key doesn't exist and value is 0. Mappings live in storage, so reads and writes are expensive. Use them sparingly. Structs group related data. A struct is a custom data type. It bundles multiple fields into a single entry. The struct for a user, as shown, bundles balance, wallet, and active. Once defined, you can use the user struct like any other type. You can store them in mappings or in arrays. Structs enable complex data modeling. Without them, you'd need separate mappings for each field. Events are off-chain notifications. Smart contracts run on-chain. Users interact with them, send transactions, and trigger state changes. But there's a problem. Contracts can't push notifications. They can't call a webhook. They can't send you an email saying someone transferred your tokens. So how do off-chain systems like websites, mobile apps, or databases know when something happens? Events are the bridge. When something important happens, your contract emits an event. This event is logged in the transaction receipt. Off-chain systems listen for those events and react. In this example, we have a deposit function. It emits the deposit event with message.sender for the person who has called the function and message.value for the amount of ETH deposited. The indexed parameter means that the parameter is searchable. Off-chain systems can filter, give me all deposit events from this user. The amount is not indexed, so you can't filter by that as efficiently. Use indexed for parameters you'll commonly filter by. Events are critical for front ends and indexes. They're how applications stay in sync with the blockchain. Every serious smart contract emits meaningful events. It's not optional, it's expected. Oops. Modifiers are a way to enforce reusable rules. A modifier is a snippet of code that runs before or instead of a function. For example, the only owner modifier. This modifier declares that the function caller must be the owner of the contract. Here it checks if the message.sender is equal to the owner. If it's false, it reverts with an error message. The underscore is a placeholder. It represents where the original function body runs. Once defined, you apply modifiers to functions. Here on our withdraw function, we've applied the only owner modifier to the end of the function definition. When someone calls withdraw, the modifier code runs first. The required check happens, and if the check passes, the underscore executes the function body. If the check fails, the transaction reverts. The underscore is literally where the function body gets inserted. Modifiers eliminate code duplication. If 10 functions need only owner checks, you write the check once in a modifier and reuse it. More importantly, modifiers are used for security critical logic. Access control, pausable mechanisms, rate limiting, these use modifiers. They are a fundamental security tool in smart contract development. Now let's build a real contract using everything we've learned. Here is a simple bank contract. It has a pragma statement at the beginning and the contract keyword signifying a contract. The name is simple bank. First, we declare some state variables. First, we have the address public owner. This is who deployed the contract. Then we have a mapping of address to UN256 public balances. This tracks balances for each user. Then we have a few events. We have a deposit event, which is emitted when someone deposits, and a withdraw event when someone withdraws. Off-chain systems listen for these. The only owner modifier ensures only the owner can call certain functions. Then we have the constructor. This is a special function that only runs once at deployment. It's useful for setting initial data values. Here, message.sender is the person deploying the contract. We store them as the owner. Then we have the deposit function. It has the payable keyword. This means that this function can receive ETH. Message.value is the amount of ETH being sent. We add this to the user's balance, then emit an event so off-chain systems know. Our withdraw function checks that a user has enough balance, reduces the balance, then transfers the ETH back to them, then emits an event. You can now deploy this contract, call deposit with ETH, check your balance is tracked, and withdraw your ETH to get it back. This is a real functional smart contract. It's not production ready, but it works. Before you deploy smart contracts, you must think about security. Always apply access control. Many vulnerabilities come from forgetting access control. If a function transfers money, modifies state, or does anything important, restrict who can call it. Be careful with storage rights. As we've discussed, storage rights are expensive and risky, but they're also risky from a security perspective. If you update storage incorrectly, you can corrupt state. Patch updates where possible and be very careful with the order of operations. Events are critical for off-chain systems. Your front end depends on events. If your contract doesn't emit events, your front end can't stay in sync. always emit events for important state changes. Index important parameters so off-chain systems can filter efficiently. One final warning. Watch for re-entrancy attacks. In Module 5, we'll cover this thoroughly. But for now, be very careful with external function calls. If you call another contract, assume it might call you back. This can cause unexpected behavior. Let's recap. Solidity is the language for Ethereum smart contracts. Every file starts with a license and pragma declarations. State variables store data permanently in storage. They're expensive to write. Functions define behavior. They read and modify state. Visibility rules, public, external, internal, and private, control who can call what. Modifiers enforce reusable rules, especially access control. Mappings are key value stores. Fast lookup and can't iterate. Structs group related data together. Enable complex modeling. Events emit logs that off-chain systems listen for. They're critical for front ends. Storage writes are the most expensive operation. Use memory for temporary data, storage for permanent state. When you write a smart contract, think constantly about, will this be expensive? Can I optimize? Who can call this? What happens if they do? Will off-chain systems know what happened? You now have the basics to write smart contracts, but there's more to learn. In Module 4, we'll dive into token standards and building more complex contracts. And in Module 5, we'll tackle security in depth. But great work completing Module 3. You're now a smart contract developer.